The James Webb Space Telescope has truly revolutionized our view of the cosmos, providing an unprecedented window into the vast tapestry of the universe. With every new observation, it transforms our understanding of cosmic history, from capturing the faint glimmers of the earliest galaxies that emerged only a few 100 million years after the Big Bang, to unraveling the intricate details of star-forming regions and the complex atmospheres of distant exoplanets. This powerful instrument, with its cutting-edge infrared vision, enables us to peer through dense cosmic dust and reveal the hidden structures of galaxies billions of light-years away. It has illuminated the turbulent nurseries where stars are born, traced the chemical fingerprints in alien atmospheres, and offered tantalizing clues about the potential for life beyond our solar system. Each discovery not only pushes the boundaries of our scientific knowledge, but also ignites our imagination, inviting us to explore a universe far more dynamic and wondrous than we ever dared to dream. Earliest galaxies near the cosmic dawn. By finding galaxies that were formed when the universe was very young, the James Webb Space Telescope has pushed the limits of what we know about the universe. Observations have shown that objects formed less than 500 million years after the Big Bang. This gives us a new way to think about how the oldest galaxies formed and changed over time. Deep field studies by James Webb use its sensitive infrared equipment to look through cosmic dust and pick up the faint light from these very early galaxies. Astronomers can now directly see the processes that controlled the early world thanks to this ability. These earliest galaxies are characterized by intense bursts of star formation, high luminosities, and unusual spectral signatures. Their light, stretched by the expansion of the universe, arrives at Earth in the near to mid-infrared range. Detailed spectroscopy conducted by James Webb reveals the presence of elements such as hydrogen, helium, and trace amounts of heavier elements. This chemical fingerprint helps scientists determine the degree of metal enrichment that occurred during the first generations of stars. The detection of heavy elements in such young galaxies indicates that massive stars had already formed, evolved, and exploded as supernovae, thereby seeding the interstellar medium with metals. These findings challenge previous models that suggested a slower pace of chemical evolution. James Webb studies also make it possible to measure the shape of galaxies at these very long distances. People used to think that early galaxies were made up of small, squished-together objects. But James Webb has found more organized patterns even at redshifts above 10. Some of these galaxies show signs of rotating and disk-like features, which suggests that the processes that lead to fully formed galaxies may have started earlier than what theoretical models had suggested. We can learn more about the mass and movement of these early systems by doing quantitative studies of light distribution and surface brightness patterns. Also, brightness functions based on these data put limits on the number of galaxies during the reionization epoch, which is the time when the first light sources reionized the neutral hydrogen that filled the universe. The imaging data from James Webb reveal the interplay between radiation from young stars and the surrounding intergalactic medium. In many cases, ionized hydrogen regions, or H2 regions, are seen around these nascent galaxies, indicating vigorous star formation and the presence of massive hot stars. The relative sizes and brightnesses of these regions help calibrate models of cosmic reionization and shed light on the feedback mechanisms that regulate star formation in low-mass galaxies. We are starting to get a full picture of the universe when it was less than 1 billion years old by taking statistical samples of these early galaxies from several deep fields. These numbers help researchers test and improve ideas about how structures form by letting them compare visible features with predictions made by cosmological simulations. The success of these findings not only shows how smart James Webb is, but also how quickly we've learned about how the universe came to be. Ultra-detailed galactic morphologies. The James Webb Space Telescope has changed the way we think about the structure of galaxies by showing us information about the shapes of faraway galaxies that we had never seen before. With its high-resolution infrared instruments, James Webb has helped scientists see parts of the structure that were hidden by cosmic dust and the limits of older observatories. Researchers can now study the shapes, sizes, and internal details of galaxies over very long cosmic distances by taking very clear pictures. These pictures give them important information about how galaxies formed and how they have changed over time. Detailed imaging from James Webb has uncovered features such as spiral arms, bars, clumpy star-forming regions, and even central bulges in galaxies that formed within the first billion years after the Big Bang. These observations challenge earlier models, which predicted that young galaxies would be small, chaotic, and largely irregular in appearance. Instead, some of these early galaxies already display organized structures that hint at the rapid development of galactic dynamics. The detection of well-defined spiral arms and coherent disk-like structures in certain high redshift galaxies suggests that the processes responsible for angular momentum distribution and star formation regulation were in place much earlier than previously believed. Spectroscopic studies help the high-resolution images by giving important details about the galaxy's chemical makeup and how they move. Astronomers can figure out the ages of stellar populations, the metallicity slopes, and the rates at which stars are forming in different areas by measuring how light is spread out across different bands. For example, the fact that some galaxies have well-developed bars shows that gravitational instability and long-term development have already changed the paths of stars. These traits are very important for pushing gas toward the centers of galaxies, which could start bursts of star formation and feed the supermassive black holes in the center. The shape information that James Webb collected also helps us make better models of how galaxies form. Quantitative data, like surface brightness profiles and structure decompositions, help us figure out how galaxies' masses are distributed and how stars formed in the past. This level of detail helps scientists make models of how the universe evolved better by bridging the gap between theory simulations and data from observations. Researchers can test different situations for galaxy mergers, the buildup of cold gas, and internal dynamical processes like disk instabilities by comparing the shapes of objects that have been seen with those that have been predicted by simulations. The ability to discern fine morphological features in distant galaxies helps trace the interplay between environment and internal dynamics. For example, in dense galaxy clusters or interacting systems, tidal forces can distort galactic shapes and trigger the formation of extended tidal tails or bridges. James Webb's sharp imaging reveals these subtle interactions, providing evidence for the role of the environment in shaping galaxies over time. The detailed morphologies offer a snapshot of how galaxies evolve from disordered clumps of stars and gas into the well-organized systems we see today. Star-forming regions in the Tarantula Nebula. The James Webb Space Telescope has changed the way we think about places where stars are born by letting us see very detailed pictures of places like the Tarantula Nebula in the Large Magellanic Cloud where stars are being born. With James Webb's infrared powers, we can see through thick clouds of gas and dust and see the complicated processes at work in one of the busiest places known for star birth. In the Tarantula Nebula, vast regions of ionized gas and swirling dust reveal a chaotic yet structured environment where new stars are emerging at an extraordinary rate. James Webb's images capture a tapestry of young, hot stars surrounded by glowing gas, highlighting the intense ultraviolet radiation that these nascent stars emit. This radiation ionizes the surrounding hydrogen, causing it to glow in distinct hues that trace out the boundaries of the nebula. The resulting emission line structures not only map the regions of active star formation, but also provide critical data on the physical conditions, such as temperature and density, within the nebula. A new type of high-resolution imaging from James Webb sheds more light on the Tarantula Nebula's complicated movements. Researchers can find out about the chemicals in an area and how they move by looking at the spectral lines that charged gas gives off. The information shows that the nebula has a lot of heavy elements, which come from stars that have died in the past. The gas cools down because of these metals, which is necessary for gravity collapse and the creation of new stars. Spectral studies make detailed velocity maps that show turbulent flows and shock fronts. These are signs that stellar winds and supernova remnants are reacting with the medium around them. It's not at all clear how the Tarantula Nebula is put together. James Webb has seen small groups of protostars buried deep in thick molecular clouds in its field of view. At these groups, you can see stars at different stages of formation, from the earliest gravitational crashes to young stars that are further along and have already started to remove their birth coats. Astronomers can study these objects on sizes that were not possible before thanks to the high spatial precision. They can track how individual protostars and their circumstellar disks change over time. These kinds of studies are very important for figuring out what conditions were like before planets formed around young stars. Detailed imagery of the Tarantula Nebula provides a benchmark for comparing star-forming regions in more distant galaxies. The interplay between massive star formation and the feedback processes, such as stellar winds, radiation pressure, and eventual supernova explosions, is a fundamental component of galactic evolution. By studying the Tarantula Nebula in our neighboring galaxy, scientists can calibrate models that predict star formation rates and feedback efficiency in the early universe. The nebula thus serves as a local laboratory for investigating the conditions that prevailed during the epoch of peak star formation in the cosmos. From what James Webb has seen of the Tarantula Nebula, we can also learn more about how the environment affects the formation of stars. When the quantity of gas is higher, the rate of star formation is much faster. This causes stellar groups to form very quickly. In turn, these groups change their surroundings through feedback loops and gravity interactions, which could start new rounds of star formation in a cycle that keeps going. Atmospheric composition of WSP-39b. WSP-39b is a hot world that looks a lot like Saturn. It has become a top target for studying its atmosphere with the James Webb Space Telescope. Astronomers have been able to study its atmosphere with amazing accuracy, thanks to detailed spectroscopic observations. These observations have shown that its atmosphere is made up of a lot of different chemicals, which goes against what we thought we knew about alien atmospheres before. James Webb's near and mid-infrared instruments pick up a lot of wavelengths that are sensitive to the chemical fingerprints in WSP-39b's atmosphere. This lets scientists find key absorbers and figure out how common they are. The spectrum from WSP-39b shows clear absorption patterns that can be linked to molecules like carbon dioxide, sulfur dioxide, and water vapor. Since water vapor is present, it shows that even though the world is very hot, it still has a lot of this important molecule in its atmosphere. In the near-infrared, water absorption lines stand out. Scientists can use their width and shape to figure out how much water is on Earth and how its temperature is distributed. Carbon dioxide can be recognized by its unique mid-infrared bands. These bands give us more information about the chemistry of the planet's atmosphere and the processes that make it up. It's interesting that sulfur dioxide was found because it shows that photochemistry or even ongoing volcanic processes are releasing sulfur compounds into the high atmosphere. James Webb's spectroscopic observations not only identify these molecules, but also measure the relative abundances, which are crucial for understanding the atmospheric dynamics and evolution of WSP-39b. For instance, the ratio of carbon dioxide to water vapor can provide constraints on the planet's carbon-to-oxygen ratio, a parameter that influences the types of clouds that form and the overall opacity of the atmosphere. This ratio is also linked to the conditions in the protoplanetary disk from which the planet formed. A higher than expected concentration of sulfur dioxide hints at vigorous photochemical reactions driven by the intense ultraviolet flux from the host star. These reactions could be breaking down more complex molecules, leading to a buildup of sulfur compounds that are otherwise not predicted in standard equilibrium models. High-precision transmission spectroscopy during the planet's transit across its star has enabled the isolation of its atmospheric signal from the overwhelming glare of the host star. This method, combined with James Webb's sensitivity, reduces contamination and reveals fine details in the spectrum that were previously inaccessible. The data also allow for the investigation of temperature-pressure profiles within the atmosphere. By fitting the observed spectral features with atmospheric models, scientists can derive the temperature gradient and the vertical distribution of the molecules, which are key to understanding heat redistribution and atmospheric circulation patterns on the planet. The results go against the old models that thought the atmospheres of hot exoplanets like Saturn would be easier and more uniform. Instead, WSP-39b has a stacked atmosphere with active photochemistry, complicated chemical interactions, and possible dynamical processes that mix the different parts of the atmosphere. The information we got from WSP-39b is very important for improving our ideas about how exoplanets form and change over time. Detailed study of brown dwarfs. Brown dwarfs cool down and fade over time because they don't have enough mass to keep hydrogen fusion going in their cores. Astronomers can keep a close eye on these cooling processes thanks to James Webb sensitivity in the near and mid-infrared bands. Scientists can follow the cooling curves of brown dwarfs and compare them to theoretical models of how substellar evolution works by looking at the heat they give off. This comparison not only helps us get a better idea of how old and heavy they are, but it also helps us understand how these things work physically. Spectroscopic studies by James Webb have shown that brown dwarfs' atmospheres are very complicated chemically. The spectra show different types of chemical absorption, such as carbon monoxide, water vapor, and methane. Methane is the main gas that brown dwarfs receive, while carbon monoxide bands are stronger in hot ones. Scientists can figure out the temperature and pressure patterns in the atmospheres and find cloud layers by looking at the depth and shape of these absorption features. These clouds, which are made up of silicates and metal oxides in hotter objects and sulfur and salt condensates in cooler ones, are very important for changing the bands that we see. By measuring these spectral traits accurately, scientists can find out how common elements are and what chemicals are in the atmospheres of brown dwarfs as a whole. High-resolution imaging provided by James Webb further enhances the study of brown dwarfs by resolving subtle variations in their brightness and color. Variability in the infrared light curves of brown dwarfs suggests dynamic weather patterns, possibly linked to rotational modulation of patchy cloud cover. These observations have sparked new discussions about the atmospheric dynamics on substellar objects, including how convection, rotation, and cloud formation interact over time. Detailed mapping of these variations helps refine models of atmospheric circulation, offering clues to how these processes might operate in both brown dwarfs and giant exoplanets. James Webb's ability to see brown dwarfs in areas where stars are being formed and in young groups gives us a look into how they evolved in the beginning. Astronomers can see how the physical qualities of brown dwarfs change from the time they are formed until they are fully grown by looking at a group of them that are all different ages. This statistical method lets us test theory models and learn more about how the masses of things beyond the stars change over time. Figuring out how the masses of brown dwarfs are spread out in different settings is crucial for understanding how stars form and the starting mass function. Brown dwarfs are great places to study things that happen in the atmospheres of both planets and stars. Scientists can study important physical and chemical processes like non-equilibrium chemistry, cloud dynamics, and radiative convective balance in these objects because their structures aren't as complicated as those of full-fledged stars. Because of this, James Webb's measurements are very important for testing and improving the models of atmospheres that are used for many different astronomical objects. Mid-infrared view of Stephan's Quintet. Stephan's Quintet is a complex system of 5 galaxies, with 4 of them physically interacting while the 5th is a background object. The mid-infrared observations by James Webb allow scientists to peer into regions heavily obscured by dust, which absorb visible light but emit strongly in the infrared. This capability is critical in revealing the structure of shock fronts, tidal streams, and regions of intense star formation that result from gravitational interactions and mergers. The infrared data show bright, filamentary structures where shock waves compress the interstellar medium, triggering bursts of star formation and heating the dust to temperatures that emit in mid-infrared wavelengths. Medium infrared spectroscopic research has given us important information about the chemicals that are present in these areas. It is easy to see the emission lines from ionized neon, sulfur, and other heavy elements. This lets experts figure out how metallic the gas is and how it is excited. Based on these measures, the shock fronts have a lot of processed matter. This means that the interstellar medium has already been improved by past generations of stars. Also, special spectral properties show that polycyclic aromatic hydrocarbons, PA8, are present, which shows how important complex organic molecules are in the process of star creation. Astronomers use the size and location of these patterns to figure out how stellar feedback affects the gas and dust around the star. The mid-infrared view of Stephan's Quintet also sheds light on the energy budget of the interacting galaxies. By measuring the thermal emission from heated dust grains, James Webb quantifies the amount of energy being dissipated in the collisions and mergers. This energy, largely released through shock heating, influences the future evolution of the galaxies by altering the physical state of the interstellar medium. Detailed mapping of the dust temperatures across different regions reveals gradients that trace the flow of energy and matter during the galactic interactions. These observations are key to understanding how collisions can both trigger and suppress star formation over cosmic timescales. Small structures inside the shock fronts can be studied thanks to James Webb's skill at resolving fine features in the mid-infrared. High-resolution imaging shows knots of light that are probably places where stars are forming now or are still forming, as well as areas where rapid mixing is clear. The shape of these structures tells us about the shock wave's size and direction, as well as how gravitational forces have changed the space between the stars. Protoplanetary disks in the Orion Nebula. By taking pictures of protoplanetary rings in the Orion Nebula in a way that has never been done before, the James Webb Space Telescope has changed our understanding of where planets come from. These disks are spinning structures around stars made up of gas and dust. They are where new planetary systems are constantly forming. High-resolution near- and mid-infrared studies by James Webb have broken through the thick clouds that block visible light, showing the detailed features of these disks and how they change over time. In the Orion Nebula, a region known for its intense star formation, protoplanetary disks, often referred to as proplids, are observed in various stages of evolution. James Webb's infrared sensitivity allows for the detection of thermal emission from warm dust grains within these disks, which is critical for mapping their structure. Detailed imaging shows that these disks are not uniform. They exhibit a range of features, including gaps, rings, and spiral arm patterns. Such structures indicate the early stages of planet formation, where gravitational interactions between the forming planets and the disk material carve out these distinct patterns. More information about the chemicals that make up the disks is needed. Emission lines from molecules like carbon monoxide, water vapor, and different organic substances can be easily seen. These lines give us information about the building blocks that could be used to make a planet. These molecules show us a picture of the disk's physical conditions, like temperature, density, and chemical gradients. These conditions are very important for understanding how solid things form from dust and gas. Researchers can find busy accretion areas, where material is falling onto the central protostar, and areas where planetesimal formation is likely to be happening by comparing the spectral fingerprints of different parts of a disk. James Webb's observations have also advanced our understanding of the interaction between protoplanetary disks and their surrounding environment. In the crowded stellar nursery of the Orion Nebula, ultraviolet radiation from nearby massive stars strongly influences the evolution of these disks. This radiation can heat the outer layers of the disks and drive photoevaporation, gradually stripping away gas and dust. James Webb's mid-infrared capabilities capture this process in detail, revealing the boundaries where the intense radiation begins to erode the disk material. These observations help quantify the mass loss rates and provide critical data for modeling the lifespan of protoplanetary disks in high radiation environments. High angular resolution images has made it possible to study disk shape on a scale that wasn't possible before. Fine structures, like narrow gaps that may have been made by planets forming, changes in brightness in certain areas, and asymmetrical disk shapes show directly how planets are formed. In some disks, you can see signs of dust grains growing and settling down. These are early signs of the formation of bigger things. Astronomers can test their ideas about how fast planetary systems can form and change in different settings by using this detailed mapping of disk features to guide their models of how disks change over time and how planets are formed. Dust and gas in the Cartwheel Galaxy. In the Cartwheel Galaxy, vast rings of material sweep outward from the core, a structure that is best explained by the density waves generated during the collision. James Webb's sensitive infrared imaging penetrates the obscuring dust that shrouds these regions in visible light, enabling astronomers to map the distribution of both cold gas and warm dust with remarkable clarity. Detailed images show that the rings are not smooth, uniform features. Instead, they are punctuated by clumps and filaments that trace the sites of active star formation. These localized concentrations of dust and gas are crucial for understanding how the collision has triggered new bursts of star formation in an otherwise disrupted environment. It has been found that molecules like carbon monoxide and ions of elements like oxygen and nitrogen give off emission lines that can be seen across the rings. It is important to know the relative amounts of these spectral patterns because they give us important information about the temperature, density, and metallicity in these areas. Some places have a lot of metals, which means that older stars have already made the space between the stars richer. This process is what keeps star formation going. The finding of molecular gas is very important because it is the stuff that new stars are made of. Researchers can figure out how fast stars are forming and compare that to theoretical models of how galaxies change after a collision by measuring the mass and spread of this gas. The collision's shock fronts can also be seen in the James Webb data. They show up as sudden changes in the ring's light and temperature. These shock fronts squeeze the gas between the stars, which causes gravity to shrink and stars to form quickly. Detailed thermal maps made by James Webb's mid-infrared tools show that the rings have different temperatures. The areas closest to the shock fronts have higher temperatures. This knowledge is very important for figuring out how well shock-induced star creation works and how long these processes last. Astronomers can study how the dust lanes and the star populations below them interact, thanks to James Webb's high precision. The complicated patterns of dust absorption and re-emission show how matter has been moving around in the galaxy since the last contact. The spectral energy patterns in different parts of the Cartwheel Galaxy help experts figure out how the collision has changed the system's shape over time and how it has changed over time. The Phantom Galaxy M74. Astronomers use M74, which is sometimes called the Phantom Galaxy, as a unique example to study how galaxies form and change over time. Even though it is called a grand design spiral galaxy, its low brightness and hazy look have made it hard to find for a long time. Thanks to the James Webb Space Telescope's James Webb high sensitivity and clarity, M74 can now show fine features of its spiral arms, star-forming regions, and dust lanes that were hidden by its dim surface before. With James Webb's infrared tools, we can see through layers of cosmic dust and see a galaxy fabric that is both complicated and mysterious. The spiral arms of M74, once only faintly detected in visible light, are now resolved with exceptional clarity. James Webb's images expose tightly wound arms that stretch outward from a modest central bulge with star-forming knots and dust lanes woven into the structure. These features indicate that M74 has maintained a steady pace of star formation over billions of years, even though its overall brightness is relatively subdued. The galaxy's phantom nature arises from its diffuse light, which challenges our ability to detect and analyze such systems using conventional telescopes. James Webb overcomes these limitations by capturing long-wavelength infrared light that highlights cooler, older stars and the interstellar medium. The data that James Webb collected helps us learn more about the surroundings around M74. The chemical makeup of the galaxy can be seen in emission lines that come from areas of charged gas. These lines show how the metallicity changes across the spiral arms. The chemical enrichment processes that have happened over the course of the galaxy's life can be seen in these variations. Finding polycyclic aromatic hydrocarbons, PAHs, in the dust lanes also gives us information about the chemical chemistry that is common in the space between the stars. Astronomers can figure out how fast stars are being formed and how well feedback loops from supernovae and stellar winds work by measuring how strong and spread out these traits are. The pictures taken by James Webb also help us understand how the diffuse population of stars is connected to the dark matter ring that controls the general structure of M74. researchers can make more accurate models of the galaxy's mass profile by making detailed maps of how the light is distributed. These maps show a dark matter component that seems to be spread out evenly. This knowledge is very important for understanding how spiral galaxies move and change over time, because it shows how visible matter and dark matter interact to create the spin curves and keep the system stable as a whole. The hazy light that first called M74 a phantom is now known to be the mark of a long, low-density stellar disk that is affected by its dark matter halo. Cosmic cliffs in the Carina Nebula. The James Webb Space Telescope has given us a view of the Carina Nebula that has never been seen before. Its detailed structure of its cosmic peaks is now very clear. Thanks to James Webb's advanced mid-infrared imaging skills, we can now see these huge, tall structures made of gas and dust that have been shaped over millions of years. The Carina Nebula's cosmic cliffs are made when strong radiation from huge stars interacts with the nebula's gravitational pull, shaping the space between the stars into dramatic, jagged shapes. This very clear picture lets us see right through to the physical processes that make stars and shape the structure of this very complicated area. In the middle of the Carina Nebula are groups of young, huge stars that give off a lot of ultraviolet light. The strong energy ionizes the hydrogen gas around it, making bright areas that show where the rocks are. The in-depth studies show a web of shock fronts and photodissociation regions, where the radiation from stars meets the thick molecular clouds. These edges are very important because they squeeze the gas and dust together, which starts new waves of star formation. Researchers can figure out how much star feedback affects the nebula's development thanks to James Webb's mapping of these structures. Along the edges of the clouds, clean emission lines from charged elements like oxygen, nitrogen, and sulfur can be clearly seen. Astronomers can use these spectral traits to find out differences in temperature, the number of electrons in a sample, and the amount of chemicals present in areas where new stars are growing. These charged gases, along with molecule traces like carbon monoxide, give a full picture of the cooling processes that help matter fall apart under the force of gravity. By measuring these lines in great detail, we can see changes in metallicity, which are very important for understanding how new generations of stars have made the space between the stars richer. A lot of research has been done on the shape of the rocks themselves. The pictures taken by James Webb show that the edges of these structures are not smooth, but have a lot of complex strands, pillars, and holes. These things show signs of hydrodynamic instability and turbulence caused by both supernova blasts and star winds. Sharp lines between areas that are lit up and areas that are dark create dramatic differences that show how the nebula's energy events have changed over time. The high spatial precision lets us look at these patterns on sizes that couldn't be reached before. This helps us understand the small-scale physics of how interstellar shocks spread and how the gas cools and breaks up afterward. Data from the Carina Nebula's cosmic cliffs are essential for constructing detailed models of star formation. By comparing the observed structures with simulations, astronomers can better constrain the parameters that govern the interaction between stellar feedback and the interstellar medium. This comparison aids in refining our understanding of how the energy from massive stars disperses and redistributes the surrounding material, influencing the formation of new stellar clusters. Ionized gas in NGC 346. Ionized gas and young star groups interact in a very complicated way in NGC 346. Massive, newly formed stars send out strong ultraviolet light that ionizes the hydrogen around them. This makes bright H2 areas that can be seen in both optical and infrared wavelength. The infrared sensitivity of James Webb is very useful here because it can see through the thick clouds of dust that cover up a lot of the area. In this way, it shows not only the general structure of the charged gas, but also the small-scale changes in temperature, density, and chemical makeup that define the area. Excitation lines like HA, O3, NN2, and SS2 can be measured in great detail by James Webb. Researchers can use the relative strengths of these lines to diagnose the gas and figure out important features about it. One way to figure out the electron density is to look at the ratio of O3 to H2. This ratio tells us about the electron temperature in the H2 regions. These factors are very important for understanding how the cooling works that lets gas fall apart under gravity and make new stars. The temperatures and densities found in NGC 346 show that stars are still forming quickly, with input from other stars and other factors affecting the process. The detection of heavy elements such as oxygen, nitrogen, and sulfur in the ionized gas is indicative of previous generations of stars that have processed primordial material into more complex elements. These measurements are vital for reconstructing the chemical evolution of the region and, by extension, the Small Magellanic Cloud. The enrichment patterns observed in NGC 346 contribute to our understanding of nucleosynthesis and the recycling of material within galaxies. In addition to spectral data, James Webb's imaging skills can produce high-resolution pictures of where the ionized gas is located. Detailed pictures show the filamentary structures, shock fronts, and bubble-like features that are made when star winds, supernova blasts, and the interstellar medium interact with each other. Not only do these structures show how huge stars release energy, but they also show how feedback controls star formation. For instance, star formation is often sparked at the edges of expanding bubbles, where gas is squeezed and heated. This suggests that stellar feedback can either stop or speed up the birth of new stars, based on the conditions in the area. The high angular resolution of James Webb allows astronomers to isolate individual star clusters within NGC 346 and study how their radiation fields influence nearby gas. This level of detail is crucial for testing theoretical models of star formation and feedback in low metallicity environments, which are common in dwarf galaxies like the Small Magellanic Cloud. Tracing organic molecules in exoplanet atmospheres. By finding and studying organic chemicals that live on these faraway worlds, the James Webb Space Telescope has made a big step forward in understanding the atmospheres of exoplanets. With its very sensitive spectroscopic tools, James Webb can measure the absorption and emission features in the near and mid-infrared wavelengths. This is where many important organic substances leave clear fingerprints. Astronomers can use these readings to figure out how much of chemicals like methane, ethane, carbon monoxide, and even more complex hydrocarbons are present. This helps them learn more about the chemistry of exoplanet atmospheres and whether or not they could support life. Observations of several hot Jupiters and warm Neptunes have revealed robust methane absorption bands in their spectra, indicating that these molecules are present in significant amounts despite the high temperatures. Methane is a fundamental building block of organic chemistry, and its detection in various exoplanetary atmospheres provides essential clues about chemical equilibrium processes and the pathways through which more complex organic compounds might form. In some cases, the relative abundance of methane compared to other molecules, such as water vapor or carbon dioxide, allows researchers to derive the carbon to oxygen ratios of these atmospheres. These ratios are crucial for testing models of planetary formation and evolution, as they reflect the composition of the protoplanetary disk from which the planet formed. James Webb has found spectral patterns that match to other organic molecules besides methane. For example, the fact that acetylene and ethane are found in the atmospheres of some exoplanets shows that their photochemistry is active, driven by the strong ultraviolet light from their mother stars. Larger molecules are broken up by these photochemical processes. This makes a chain reaction of organic chemicals that can build up in the upper atmosphere. Scientists can narrow down the reaction rates and routes that control these complicated chemical networks by comparing the spectra that have been seen with measurements made in the lab and models of the atmosphere. James Webb's ability to take high-resolution spectra over a wide range of wavelength has also made it possible to study in great detail how temperature and pressure change in the atmospheres of other planets. Changes in the depth and shape of absorption features at different wavelengths tell us about how organic molecules are arranged vertically. For instance, molecules that are more absorbed at certain wavelengths might be more concentrated in the lower atmosphere, where the pressure and temperature are better for keeping them stable. On the other hand, finding certain things in the upper atmosphere can show how photodissociation or vertical mixing processes are working to move molecules from lower levels to higher ones. In some exoplanets, thick cloud decks or photochemical hazes can obscure or mute molecular absorption features. Detailed spectral analysis helps disentangle these effects, allowing researchers to estimate the optical thickness of cloud layers and assess their impact on the overall atmospheric composition. This is particularly important for understanding the energy balance and climate dynamics of exoplanets, as clouds and hazes play a significant role in regulating temperature and weather patterns. Comparative studies of the atmospheres of many different exoplanets have shown that the organic chemistry is not all the same. The variety of molecular abundances and the way that temperature and photochemical processes affect each other show how complicated planetary atmospheres are. These results not only help us improve our models of atmospheric chemistry, but they also set the stage for future research into the possibility of prebiotic conditions, or even biosignatures, on exoplanets that are warmer and rocky. Finding heavy elements in early galaxies. Astronomers can now find and measure heavy elements in galaxies from the early universe thanks to the James Webb Space Telescope. This gives us new information about how quickly chemicals became more abundant after the first stars formed. James Webb sees the faint spectral lines that elements like oxygen, nitrogen, iron, and carbon give off by looking at faraway galaxies at high redshifts. In astronomy, these heavy elements are called metals as a group. They are made in the cores of huge stars and spread out into the space between stars by supernova blasts and stellar winds. Finding them in galaxies that formed less than 1 billion years after the Big Bang goes against what scientists thought before, which said that chemicals evolved more slowly. As light from early galaxies is redshifted, the spectral signatures of heavy elements shift into the infrared portion of the spectrum. Instruments like NIRSpec and MIRI have provided the sensitivity and resolution necessary to detect these lines, even in galaxies with relatively low luminosities. Detailed analysis of these emission lines allows astronomers to estimate the metallicity of early galaxies, which in turn offers clues about the star formation histories and the initial mass function during these formative epochs. Finding heavy elements in early galaxies also helps us understand how well the first stars made and spread metals. The presence of elements like oxygen and iron in these young systems shows that huge stars evolved quickly and ended their lives in strong supernovae. These events not only added metals to the gas around them, but they also pushed nearby molecular clouds together, which was a key part of starting more star formation. It has been seen that the metallicities in these faraway galaxies are often higher than what earlier theoretical models suggested. This means that star formation and chemical enrichment may have been more efficient than was thought. James Webb's integral field spectroscopy can be used to make a map of how heavy elements are distributed in early galaxies. These maps show differences in metallicity that help us understand how these galaxies are moving and changing inside. In some cases, the center areas have higher metal abundances than the edges. This suggests that early enrichment may have been largely caused by rapid, centralized bursts of star formation. These kinds of gradients are very useful for trying computer models of how galaxies form and for learning how input from young stars and supernovae controls how galaxies are put together. Astronomers can figure out how the universe evolved over time by comparing the amounts of heavy elements in early galaxies and more developed systems in our own universe. These comparison studies help us figure out how fast the world changed from being completely pure and lacking in metals to being full of different chemicals. The effects go beyond what we know about how planets form, because metals are important parts of the building blocks of terrestrial planets and the cores of gas giants. Refining the Hubble constant debate. In the past, readings of the Hubble constant have been different based on how the observations were made. Some methods, like those that use studies of Cepheid variable stars and supernovae in the local universe, give results that are different from what can be figured out from the microwave background radiation of the universe. James Webb's improved deep field images and high-resolution spectroscopy skills are now helping us narrow these differences and get a better sense of how the universe is expanding. A big part of the argument is the need for accurate distance readings to galaxies that are very far away. James Webb can find and identify individual stars in faraway galaxies with unprecedented sharpness because it is sensitive in the infrared range. Astronomers can get much better ideas of how far away things are by precisely measuring how bright standard candles, like Cepheid variables and type Ia supernovae, are. The estimated rate of expansion of the universe is changed directly by these more accurate readings. The Hubble constant's gaps can be lowered by getting more accurate distances. This will help bring together differences in readings from the early universe and the local universe. James Webb's deep field observations extend our reach into the early universe, providing a direct glimpse at galaxies that formed just a few 100 million years after the Big Bang. By analyzing the redshifts of these ancient galaxies, scientists can trace the expansion history of the universe over time. This method offers an independent check on local measurements and helps build a more coherent picture of how the expansion rate has evolved. The ability to detect faint, distant galaxies means that James Webb can contribute to a more precise calibration of the distance ladder, a critical step in resolving the Hubble tension. Researchers can find out important things about these galaxies, like how fast stars are forming, how metallic they are, and how they move inside by looking at spectral lines and how light is distributed within them. These features are used in cosmological models and help us learn more about the processes that cause big structures to change over time. In turn, this better knowledge changes the ways that cosmic lengths are measured, which gives the value of the Hubble constant more weight. Cross-calibration with other tools and observational methods is possible thanks to James Webb's high-precision photometry and spectroscopy across a wide range of bands. This multi-wavelength method is necessary to find and fix systematic mistakes that might have thrown off earlier readings. When James Webb works with other observatories, like the Hubble Space Telescope and sites on the ground, it makes it easier to settle the Hubble constant issue. Because of what James Webb has done, data from different methods are coming together. James Webb is helping to close the gap between local and cosmological estimates of the rate at which the universe is expanding by making distance measurements more accurate and extending the observational baseline to earlier cosmic epochs. Carbon dioxide on rocky exoplanets. Finding and measuring carbon dioxide, CO2, a gas that is very important to the temperature and chemistry of the Earth's atmosphere, is one of the most important parts of these studies. CO2 is not only a sign of natural activity on rocky exoplanets, but it can also show if the planet might be habitable. It does this by showing how surface conditions and atmospheric processes are connected in complex ways. By observing exoplanet transits and eclipses, astronomers can isolate the light that filters through or is emitted by an exoplanet's atmosphere. The resulting spectra display distinct signatures of CO2, along with other molecules such as water vapor and methane, which together paint a comprehensive picture of the atmospheric composition. In particular, the absorption bands around 4.3 microns are indicative of CO2 presence and allow scientists to determine its abundance relative to other atmospheric constituents. The detection of carbon dioxide on rocky exoplanets has profound implications for our understanding of their climate systems. On Earth, CO2 is a key greenhouse gas that regulates surface temperatures by trapping heat. Similar processes are expected to occur on exoplanets, where the concentration of CO2 may determine whether a planet experiences a runaway greenhouse effect or maintains temperate conditions that could allow liquid water to exist. By comparing the observed CO2 levels on different rocky exoplanets, researchers can assess the likelihood of diverse climate states and evaluate how planetary atmospheres evolve over time. James Webb's skill to describe CO2 is very important for learning about the geological past of other worlds. CO2 can be made by volcanoes and reused by weathering processes on worlds that are made of rock. The way a planet's atmosphere changes depends on how well these processes work together. A lot of carbon dioxide could mean that there are active volcanoes or not enough effective ways to store carbon. On the other hand, smaller amounts could mean that the carbon cycle is fully developed and keeping the climate stable. From light years away, these kinds of readings give us indirect clues about the inside of a planet and its geological action that are hard to get any other way. In addition to its role in climate regulation, Carbon dioxide also serves as a benchmark for the potential for biosignatures. In some cases, an atmosphere with an anomalously high or low CO2 concentration relative to expected equilibrium models could hint at biological processes that alter the atmospheric chemistry. James Webb's precise measurements allow for the detection of these subtle deviations, providing a pathway for identifying planets where life might influence atmospheric composition. Detailed atmospheric models, calibrated with James Webb observations, are now able to simulate a wide range of planetary conditions. By incorporating CO2 absorption data, temperature profiles, cloud formation, and circulation patterns on rocky exoplanets. Insights into quasar-host galaxies. People have known for a long time that quasars, the very bright centers of galaxies that are driven by supermassive black holes accreting matter, are signs from far away in the universe. Astronomers can see through the bright central quasar with James Webb's improved infrared powers and see the structure of the host galaxy below. This gives us important information about how black holes and their galactic environments change together over time. By targeting quasars at high redshifts, James Webb has enabled the study of host galaxies formed during the peak of cosmic activity. Detailed imaging reveals that many quasar-host galaxies exhibit signs of rapid star formation, disturbed morphologies, and significant dust obscuration. The infrared wavelengths captured by James Webb can penetrate the dense dust clouds that typically hide these galaxies from optical view, exposing stellar populations and structural features that provide clues to the galaxy's assembly histories. High-resolution images show tidal features, merger remnants, and disk-like structures that suggest these galaxies are undergoing dynamic interactions. Such observations help to confirm theoretical models in which galaxy mergers and interactions trigger both star formation bursts and the growth of central supermassive black holes. Ionized gas emission lines, such as those of hydrogen, oxygen, and nitrogen, are used to find out how the gas moves, how metallic it is, and what state of ionization it is in. These results show that feedback from the active galactic center, AGN, is very important for controlling star formation because it heats up and pushes gas out of the central regions. The relative strengths of different spectral lines also show that these galaxies are rapidly chemically enriching. This suggests that there have been intense, short-lived star formation events that have left their mark on the medium between the stars. Researchers have been able to figure out how the center AGN affects the stars around it, thanks to James Webb's ability to map out where the dust and gas are located within quasar hosts. The way that dust is absorbed and released in space shows how the winds from quasars interact with the material in the home galaxy in complex ways. Clear signs of outflows, which are huge streams of gas moving quickly away from the center, have been found in several systems. These streams not only help control the black hole's growth by reducing the fuel that can be accreted, but they also change the galaxy's chances of forming stars in the future. By measuring how much mass and kinetic energy these winds have, scientists learn a lot about the feedback loops that affect how galaxies change over time. James Webb's observations have also led to more accurate measures of the star masses and luminosities in the host galaxies. When you mix detailed photometric studies with advanced modeling methods, you can figure out how stars formed and how their ages are spread out in groups. So, this helps us figure out how fast these galaxies gained mass and how the growth of the center black hole is connected to the galaxy's overall history. Observations of green pea galaxies. Green pea galaxies are a type of dense, heavily star-forming galaxies that can be identified by their distinctive green look in optical surveys. The James Webb Space Telescope has made groundbreaking studies of these galaxies. Scientists first found these galaxies through citizen science projects. They are small, have low mass, and make a lot of stars quickly. This makes them great places to study how galaxies formed and how the universe ionized. They are showing details about their internal structures and areas where stars are being formed that were hidden by dust and a dim surface. Spectroscopic studies pick up strong emission lines like O3 and HB, which not only dominate their visual spectra, but also tell us a lot about the interstellar medium's ionization state and metallicity. These emission lines show that green pea galaxies are home to big young stars that give off strong ultraviolet light that quickly ionizes the gas around them. The high-resolution imaging capabilities of James Webb have uncovered that these galaxies possess clumpy structures, with concentrated pockets of star formation. The spatial distribution of star-forming knots within green pea galaxies suggests that their intense activity is not uniformly distributed, but rather localized in dense regions that drive their overall luminosity. This patchiness has important implications for understanding the escape fraction of ionizing photons, which is crucial for determining the role these galaxies may have played in ionizing the intergalactic medium during the early universe. The low metallicities seen in many green pea galaxies are similar to conditions in the early universe. This makes them good models for the primordial galaxies that helped ionize the universe. Scientists can figure out how common elements like oxygen and nitrogen are by looking at the amounts of different emission lines. These findings give us clues about how nucleosynthesis worked in the earlier stars and help improve models of how chemicals change over time in galaxies with low masses. Even though these galaxies are relatively dust-poor compared to more massive systems, the presence of dust can still affect the escape of ultraviolet radiation. Infrared observations help quantify this effect by mapping the distribution and temperature of dust, thereby improving our understanding of how these galaxies contribute to the reionization process. When James Webb combines high spatial resolution imaging with sensitive spectroscopy, he gets a full picture of green pea galaxies. These observations not only show how strong star formation works on the inside, but they also let us compare them to theoretical models that explain how early galaxies changed over time. Clumping of dark matter in galaxy clusters. By utilizing its high-resolution imaging and spectroscopic capabilities, James Webb enables astronomers to map the gravitational effects of dark matter on the visible components of clusters with unprecedented precision. Instead of observing dark matter directly, scientists infer its presence through gravitational lensing, the bending of light from background galaxies as it passes near a massive galaxy cluster. This effect provides critical insights into how dark matter is clumped and distributed on various scales within clusters. Dark matter is thought to make up a big part of the mass in galaxy groups, much bigger than the mass of stars and hot gas. Researchers can make accurate mass maps of these groups thanks to James Webb's ability to take clear pictures of lensed galaxies. Astronomers can figure out the cluster's gravitational pull by looking at how the shapes of hundreds of background galaxies have changed over time. These maps of mass show that dark matter is not spread out evenly. Instead, it is clumped into substructures, or halos, that follow the path of the galaxies and intergalactic gas in the cluster. James Webb's high-precision readings of gravitational lensing have shown that dark matter clustering is structured in a hierarchy. Each galaxy in a galaxy cluster has its own dark matter halo around it. These halos are part of a bigger, more widespread dark matter envelope that surrounds the cluster. Studies that go into great detail show that these subhalos have different amounts of mass and concentration. Some are thick and close together, while others are spread out. This level of detail is a very important test for dark matter theories, especially those that are based on the cold dark matter, CDM theory. Differences between what we know about halo features and what simulations say they should be can help us figure out what dark matter particles are and how they interact with each other. By comparing these dynamical mass estimates with mass maps derived from lensing, astronomers can test the consistency of different methods and refine the overall mass profile of the cluster. Any deviations may indicate complex interactions between dark matter, galaxies, and the intracluster medium, shedding light on the underlying physics governing structure formation in the universe. Detailed imaging of clusters reveals how dark matter clumps can affect the spatial distribution and morphology of the galaxies they host. In regions with high dark matter concentration, gravitational forces can lead to accelerated merging and the formation of central dominant galaxies. These processes, driven by dark matter dynamics, have significant implications for the assembly history of clusters and the overall evolution of large-scale cosmic structures. The amount of heat in the intra-cluster medium is also affected by how dark matter is clumped together. When dark matter halos join and interact, they can make the hot gas around them shake and swirl. Astronomers can study how dark matter-induced dynamics affect the heating and cooling processes, sensitive mid-infrared devices to pick up on the gas's weak thermal emissions. Characterizing debris disks around young stars. As a result of planet formation, debris rings are made up of dust, gas, and small pieces of rock. Scientists use them as labs to study the processes that control how planetary systems change over time. James Webb's sensitive infrared devices pick up the disk's heat emissions, which show what they are made of, how they've changed over time, and how they are structured. In the mid-infrared range of light, scientists have found that silicate grains, carbon-rich materials, and even more complex biological molecules have their own unique properties. These spectrum fingerprints tell us a lot about the minerals in the disk and show that the dust grains are constantly being changed by collisions, sublimation, and accretion. Crystalline silicates, for instance, show signs of thermal processing and annealing events, suggesting that the disk has a past of burning and reforming. The morphology of debris disks, as revealed by James Webb, often exhibits intricate structures such as rings, gaps, and asymmetries. These features are of particular interest because they can indicate the presence of forming planets that are gravitationally sculpting the disk. High-resolution observations have resolved narrow ring-like features and sharp inner edges that point to the action of planetary bodies clearing their orbits. By analyzing the brightness profiles and color gradients across these structures, researchers can infer the size distribution of dust grains and the efficiency of the collisional processes that generate them. This level of detail is critical for testing models of planet formation and for understanding how young planetary systems evolve over time. Astronomers can make temperature maps by looking at changes in the disk's thermal output. These maps give them clues about how the disk is heating up. The center of the disk is usually warmer than the edges because it is closer to the star that hosts it, while the edges are much cooler. These differences in temperature are very important for understanding the physical factors that change the makeup of dust grains, like how volatile chemicals condense and sublimate. Using these data to make more accurate temperature models helps us learn more about the disk's vertical structure and density distribution. Another critical aspect of debris disk characterization is the study of transient phenomena, such as dust clumps and asymmetrical features that may arise from recent collisions. James Webb's capability to monitor these disks over time offers a unique opportunity to observe the short-term evolution of these features, providing direct evidence of the dynamic processes governing dust production and removal. By tracking these changes, astronomers can estimate the timescales for collisional cascades and assess the overall stability of the disk environment. Keeping an eye on the debris rings that form around young stars helps us learn more about how planets form in the galaxy as a whole. Researchers are able to compare the features of disks in different stellar environments and at different ages by putting together data from a statistically significant group of stars with debris disks. This comparison helps us understand how disks change over time and finds the starting conditions needed for planets to form. Rare Wolf-Rayet stars in detail. These stars, which show a short but important part of the life cycle of the heaviest stars, teach us a lot about how stars change over time, how nucleosynthesis works, and how the medium between stars gets richer. Astronomers can look into the complicated atmospheres of Wolf-Rayet stars and study the processes that cause them to lose a lot of mass with the help of James Webb's high-resolution infrared spectroscopic tools. Wolf-Rayet stars exhibit spectra dominated by broad emission lines of helium, nitrogen, carbon, and sometimes oxygen. These features arise from the outer layers of the star, which are being expelled at speeds of up to several thousand kilometers per second. James Webb sensitivity allows for detailed measurements of these emission lines, providing direct constraints on the wind velocity, density, and temperature profiles of these stars. By analyzing the line profiles, researchers can determine the mass loss rates with unprecedented precision, which is crucial for modeling the evolution of massive stars. High mass loss rates significantly influence the future evolution of these stars, affecting their transition into supernova or even gamma-ray bursts. Along with their periodic features, Wolf-Rayet stars' chemical makeup can also tell us about the nuclear processes going on inside their cores. As the star's top layers come off, the results of nuclear fusion can be seen on the surface. The spectrum readings from James Webb show how much helium, nitrogen, carbon, and oxygen there is. This supports the CNO cycle and other advanced fusion processes that have happened in the core of stars. These data not only help figure out what stage of growth each Wolf-Rayet star is in, but they also help scientists make models that show how these stars add to the chemical richness of the galaxies they live in. Heavy elements thrown out by Wolf-Rayet winds are a big part of what makes the cosmic medium metallic, which affects how stars form in the future. James Webb's imaging and spectroscopic observations have also revealed spatially resolved structures in the environments of Wolf-Rayet stars. Many of these stars are surrounded by nebulae composed of material ejected during previous episodes of mass loss. These nebulae, often visible as intricate shells or bubbles, provide a record of the star's recent evolutionary history. By mapping these structures in the infrared, astronomers can trace the distribution and composition of the ejected material. The morphology of these nebulae, along with their chemical makeup, offers insights into the interactions between the stellar wind and the surrounding interstellar medium, as well as the processes that drive the shaping of circumstellar environments. Wolf-Rayet stars are also important to study because they can start supernovae and long-duration gamma-ray bursts. Because they lose a lot of mass and are very bright, they are likely to have explosive ends that have big effects on the galaxies that house them. James Webb's observations help us figure out what these stars were like before they went supernova. For example, we can figure out how much mass they lost and what chemicals were on the surface. Ultraviolet light surrogates in the infrared. It can be hard to see UV light directly in some places because of dust, redshift effects, or device limits. James Webb found a way to see UV light indirectly by catching its signatures in the infrared. With this new discovery, scientists can look into things like the rates at which stars grow, the conditions of ionization, and energetic feedback processes in places that they couldn't see before. Utilizing infrared light instead of UV light has many benefits, one of the main ones being its ability to pass through thick clouds of dust. In places like active galactic centers and galaxies that are forming stars, dust absorbs and scatters UV photons, making it hard for regular UV binoculars to see what's going on below. But James Webb's infrared tools can pick up the energy that dust heated by UV light sends back out into space. Researchers can figure out what the high-energy world was like in the beginning by using this thermal output as a good substitute for measuring the amount and spread of UV radiation. Astronomers can figure out how many new stars are forming and whether there are any young, huge stars that would normally dominate the UV output by looking at the spectral energy distribution in the mid-infrared. James Webb's infrared spectrometers also pick up important emission lines that directly show how UV-driven processes work. As an example, cosmic redshift moves lines from ionized carbon, oxygen, and nitrogen into the infrared for galaxies far away. These lines are usually used to measure the physical conditions in H2 areas. It is possible to figure out the ionizing photon flux, which in turn gives us an idea of how bright a galaxy is in ultraviolet light. Thanks to James Webb's ability to measure these lines very accurately, it is very important to be able to do this when studying the early universe, because space and other matter make it hard to directly observe UV light. By comparing infrared data with UV observations from other telescopes, researchers can calibrate models that describe the interaction between high-energy radiation and the interstellar medium. These models help to determine how efficiently dust grains absorb UV light and re-emit it in the infrared. Such calibrations are essential for accurately measuring star formation rates and for understanding the feedback mechanisms that regulate galaxy evolution. The ability to bridge the gap between UV and infrared wavelengths provides a more holistic view of the energy budget in galaxies and refines our estimates of how much energy is produced by young stellar populations. James Webb's better spatial clarity is another big benefit of using infrared light instead of UV radiation. A lot of the time, UV images aren't clear enough to see small details in places where stars are forming, or in the narrow line regions around active galactic centers. James Webb's high-resolution infrared imaging shows the exact shapes of these areas, which lets scientists map the spread of UV-driven processes with a level of detail that has never been seen before. Fluorine detection in dying stars. Looking closely at dead stars, especially those in the asymptotic giant branch AGB phase, shows that they have small amounts of fluorine in their bands. Fluorine is a very rare element in the universe, but it is very important for understanding nucleosynthesis and how galaxies change chemically over time. For the first time, James Webb's very sensitive spectroscopic tools have clearly found fluorine lines in the infrared spectra of these evolved stars. This gives us new information about what happens in the last few stages of stellar evolution. AGB stars are characterized by their extensive pulsating atmospheres and the efficient dredge-up of material from the interior, where nuclear reactions occur. As these stars near the end of their lives, complex fusion processes take place in their cores, including the helium-burning shell, which produces fluorine as a byproduct. The detection of fluorine is significant because it serves as a diagnostic of the nucleosynthetic pathways in these stars. James Webb's observations have targeted specific infrared wavelengths, where fluorine exhibits distinctive absorption features, enabling astronomers to measure its abundance with unprecedented accuracy. With James Webb's high spectral precision, it is possible to separate weak fluorine lines that are usually mixed with other chemical features in the spectrum of cool, extended atmospheres. Researchers can figure out how much fluorine is in the galaxy by resolving these traits and comparing the results to theoretical models of how stars form and evolve. Early data show that the amount of fluorine in some AGB stars is higher than what was expected by standard models. This suggests that other ways of making fluorine, like neutron capture processes during thermal pulses, may play a big role. These findings make us think again about the nucleosynthetic output of AGB stars and how they contribute to the chemical enrichment of the galaxy. High-resolution imaging in the infrared reveals that fluorine is not uniformly distributed. Rather, it appears concentrated in regions where dust formation is active. This correlation between fluorine-rich regions and dust indicates that the element may be incorporated into dust grains as the star expels its outer layers. By studying these spatial variations, astronomers can trace the mass loss history of AGB stars and assess how effectively they pollute the interstellar medium with newly synthesized elements. Finding fluorine in dying stars also changes how we think about how chemicals change in the universe as a whole. The Milky Way and other galaxies have a lot of fluorine because AGB stars lose mass and add to the amount of fluorine in the medium around them. Getting accurate measures of how much fluorine is made in AGB stars is important for calibrating models of chemical evolution. This is especially true for understanding the known fluorine to oxygen ratios in different galactic environments. For studying the lifespan of elements and the processes that change star populations over very long periods of time, these numbers are very important. Cloud layers on gas giants. The study of cloud layers on gas giants is critical for understanding the atmospheric dynamics and thermal structure of these massive planets. With the James Webb Space Telescope, astronomers are now able to probe the intricate details of these cloud formations with unparalleled sensitivity and resolution. James Webb's advanced infrared instruments provide data that elucidate the composition, vertical structure, and spatial variations of clouds on planets like Jupiter and Saturn, revealing layers of complexity that were previously hidden from view. In order to comprehend the thermal structure and atmospheric dynamics of these enormous gas giants, research into their cloud layers is essential. Astronomers can now look into the finer aspects of these cloud formations with a level of sensitivity and clarity that has never been seen before thanks to the James Webb Space Telescope. James Webb's high-tech infrared devices collect information about the makeup, vertical structure, and spatial changes of clouds on planets like Jupiter and Saturn. This opens up new levels of complexity that were not visible before. On Jupiter, for example, there are multiple cloud decks that exist at different altitudes, each corresponding to a specific chemical species. The uppermost layer is primarily composed of ammonia ice, which reflects much of the incoming sunlight and contributes to the planet's characteristic brightness in the visible and near-infrared. Beneath this, deeper layers may consist of ammonium hydrosulfide clouds and water clouds, which are much thicker and can influence the planet's thermal emission. James Webb's ability to differentiate between these layers through high-resolution spectroscopy has provided a clearer picture of how these clouds interact with the underlying thermal structure, affecting both radiative transfer and convective processes within the atmosphere. The lightning-fast spinning and strong zonal winds that describe gas giants change how these cloud layers move. Observations with James Webb have shown how these winds tear and change the shape of clouds, creating bands, swirls, and turbulent eddies. Researchers can figure out wind speed profiles and the patterns of airflow across different latitudes by studying Doppler changes in the spectral lines of key molecules. These data are very important for testing and improving global circulation models that try to explain how cloud patterns move around and change over time. Clouds change over periods ranging from hours to days, as shown by the fact that gas giants are constantly being watched. Changes in cloud shape and brightness can be connected to things like convective upwelling, wave propagation, and localized storm activity. These quick changes are very important for learning about how energy moves through the atmosphere and the feedback loops that keep weather systems going or break them down. Methanol and water in cometary nuclei. The James Webb Space Telescope has revolutionized our understanding of cometary nuclei by revealing detailed chemical composition, particularly the presence and distribution of methanol and water. These observations provide key insights into the primordial materials that formed our solar system and continue to influence its evolution. Comets, often considered as time capsules of the early solar system, contain volatile compounds that have been preserved in deep freeze for billions of years. With James Webb's advanced infrared spectroscopic capabilities, astronomers are now able to probe these ancient bodies with unprecedented sensitivity, measuring subtle spectral features that indicate the presence of methanol, water, and other key molecules. Infrared observations of cometary nuclei enable the detection of characteristic absorption bands associated with water ice and methanol. Water, the most abundant volatile in comets, exhibits distinct absorption features near 3 microns, while methanol shows prominent bands around 3.4 and 9.7 microns. By analyzing these bands, scientists can determine the relative abundances of these compounds, as well as infer their physical state, whether they exist as crystalline or amorphous ice. This distinction is critical, as the structure of water ice affects how comets evolve under solar heating during their journeys through the inner solar system. It is possible to map chemical differences across the nucleus thanks to James Webb's ability to take high-resolution spectra. Spectroscopic mapping shows that the methanol and water are not spread out evenly. Instead, areas with higher levels of methanol may show where there has been localized thermal processing or recent sublimation events. Water ice spots can show where the original, less processed material is. Such changes in space give us clues about how the comet formed and how it has changed over time. The way that water and methanol interact with each other can also help us understand the chemistry processes that made organic molecules in the early solar system. When it comes to prebiotic chemistry, methanol is one of the most basic alcohols. It helps make more complex chemical molecules. Seeing comets get closer to the Sun has shown that melting processes cause big changes in the cores. Comets get warmer as they get closer to the Sun. This makes the ices melt, releasing gas and dust that make up the coma and tail. James Webb's mid-infrared devices have shown how these processes change over time. By watching how the spectral features of water and methanol change over time, scientists can see how quickly these volatiles evaporate, and how the gas jets that form affect the comet's spin and the shape of its surface. This change over time is very important for knowing what comets do and how jets form. Finding methanol and water in the cores of comets has bigger implications for the study of how the solar system came to be. These chemicals are thought to be the most basic building blocks for life. The fact that these volatiles are still present in comets suggests that they may have been very important in bringing water and organic molecules to the early Earth, which may have helped life begin. By looking at the chemical makeups of various comets, James Webb helps to figure out the gradient of volatile distribution in the protoplanetary disk and evaluates the chance that comets could bring important materials to Earth. Better distances to lenses in gravitational lens systems. James Webb takes clear pictures of lensed galaxies and arcs that help scientists get a better idea of how far away the main lensing galaxies and background sources are. These better measures are very important for lowering the uncertainty in models that show how mass is distributed in galaxy groups and for limiting what dark matter halos are made of. Gravitational lensing occurs when a massive foreground object, such as a galaxy or galaxy cluster, bends the light from a more distant background source. The degree of light bending is directly related to the mass of the lensing object, but accurate modeling also requires precise distance measurements. Traditional methods of distance estimation, such as using standard candles, have inherent uncertainties, particularly for distant or dust-obscured objects. James Webb's near and mid-infrared observations penetrate dust and reveal details that are often missed in optical wavelengths, providing a clearer view of the lensed structures. By making it possible to see the fine features of Einstein rings and gravity arcs, James Webb makes it easier to make detailed maps of the lensing galaxies' masses. To figure out how dark matter is distributed in these systems and to calibrate the mass-to-light ratio, we need these mass maps. Astronomers can use more accurate distance readings to make lensing models that better match the forms and locations of images that have been magnified. These kinds of models depend on exact geometric constraints. Even small mistakes in distance can cause big changes in the estimated mass distribution. These doubts are lessened by James Webb's data, which makes it easier to figure out the Hubble constant and other cosmic factors. Redshift, which counts how much light has stretched because the universe is expanding, is a clear way to tell how far away something is in a universe that is expanding. James Webb's sensitive devices can find faint spectral lines in lensed galaxies at very high redshifts. This helps to improve predictions of redshift and, by extension, distances. These spectroscopic redshifts are used to check optical redshift predictions made from imaging data, making sure that all methods are consistent. James Webb's high angular sharpness makes it possible to study lensing devices on a smaller scale. This makes it possible to find parts of the lensing galaxy that might change how the lensing is set up overall. To find these substructures, like dark matter groups or satellite galaxies, you need to know exactly how far away they are so you can separate their individual elements. Better readings of distance make it possible to make more accurate models of these complicated systems. These models help us understand how galaxies grow in a hierarchy and how dark matter is distributed on both large and small scales. We can better understand the cosmic distance ladder now that we have better ways to measure distance. Gravitational lensing is a separate way to measure lengths that are beyond what can be done with normal methods. Thanks to James Webb's findings, we can directly compare distances found by lensing to those found by other means, like Cepheid variables or type Ia supernovae. In order to fix present tensions in cosmological data, especially the differences in the Hubble constant, this cross-calibration is necessary. Thermal signatures of hot asteroids. These small rocks, most of which are in the asteroid belt or move through space close to Earth, heat up and cool down quickly as they move around the Sun. The infrared powers of James Webb let scientists measure the thermal fingerprints of these asteroids. This gives them important information about the asteroid's surface compositions, rates of spin, and thermal properties. Observations in the mid-infrared range show how the surfaces of asteroids are heated by the Sun and cooled by radiation. When an asteroid spins, the side that faces the Sun quickly gets hot and sends out thermal radiation that James Webb can pick up. The temperature of the surface, and by extension, the makeup and structure of the regolith, are directly linked to the peak of this emission and its spectral shape. Scientists have used high-resolution thermal imaging to make a map of the asteroid's surface temperature changes. The map shows areas with high thermal inertia, which could be bare rock or solidified material, and areas with low thermal inertia, which could be a thicker layer of fine protective dust. Detailed thermal measurements not only provide clues to surface composition, but also help in determining the physical properties of asteroids. By modeling the observed thermal light curves, researchers can derive key parameters such as the rotation period, shape, and even the roughness of the surface. These properties are critical for understanding the formation and evolution of asteroids, as well as assessing potential hazards for near-Earth objects. For example, an asteroid with a high thermal inertia may indicate a more coherent monolithic structure, while a lower thermal inertia could signal a rubble pile composed of loosely bound fragments. James Webb's observations allow for such distinctions to be made with unprecedented accuracy. Thermal signatures of hot asteroids provide insight into the space weathering processes that alter their surfaces over time. Continuous exposure to solar radiation, micrometeorite impacts, and cosmic rays gradually modifies the optical and thermal properties of an asteroid's surface. These processes can lead to the formation of a regolith that has different thermal characteristics compared to fresh, unweathered material. By comparing the thermal emission of various asteroids, James Webb is helping to construct a timeline of surface evolution, offering a clearer picture of how these bodies age in the harsh environment of space. James Webb is also sensitive enough to find short-lived heat events on asteroids. For example, rapid bursts of activity, which could be caused by a problem with spinning or the release of volatile materials, can cause the surface temperature to rise for a short time. Getting pictures of these events in real time gives us a moving picture of how asteroids behave and helps us figure out how they are built inside and whether they could release gases. Such short-lived events help us learn a lot about the processes that cause changes on these small bodies, especially for asteroids that might be about to break apart or change the shape of their surfaces. Researchers are making statistical models of asteroids' thermal qualities by carefully studying a lot of different ones, from those close to Earth to those in the main belt. These models are very important for helping us learn more about asteroids in general, like how they affect the zodiacal light and how they are leftovers from when the solar system was young. Refining mass estimations of interstellar objects. Interstellar objects like Oumuamua and 2I/Borisov are space rocks that came from outside our solar system. They are very rare chances to study things that have passed through interstellar space. Finding out the exact masses of these objects is important for figuring out what they are made of, how they form, and the dynamical processes that push them out of their parent systems. Astronomers can use James Webb's sensitive infrared equipment to pick up on the weak heat emissions from objects in the interstellar medium as they move through the solar system. These temperature signals tell us a lot about an object's size and albedo, which are both important for figuring out its mass. Researchers can figure out what the object is made of and how it looks by watching its infrared light curve as it spins. The combination of thermal modeling and brightness measurements allows for more accurate calculations of the object's effective radius. When these measurements of radius are combined with theories about density based on spectral features, they directly lead to more accurate predictions of mass. Infrared spectra show how different ices and minerals absorb light, which gives information about what the item is made of. Having water ice, silicates, or organic substances around can show a density range that is typical of comets or hard asteroids, for instance. By setting limits on the object's density, scientists can get more accurate predictions of its mass from its size. The ability of thermal emission data and spectral analysis to work together is very important because these objects are often irregular and tumbling, which makes normal visual views less dependable. Tracking the non-gravitational forces working on cosmic objects is another new idea made possible by James Webb. As these objects move through the solar system, flammable materials can escape or sublimate, which can cause accelerations that aren't caused by gravity alone. Scientists can figure out how much mass was lost due to outgassing and make changes to the total mass estimate by keeping a close eye on these variations using James Webb's astrometric tools. works especially well for interstellar visitors that look like comets, since losing mass changes an object's speed a lot over time. James Webb's ability to look at these things over a wide range of bands also makes sure that the data he collects covers the full range of their thermal emission spectrum. This widespread reduces the number of unknowns in the temperature models that are used to figure out size and, by extension, mass. The high signal-to-noise ratio of James Webb's data puts strong limits on the physical factors that are used in mass estimation methods. This lets us tell the difference between things that look the same but have different densities and compositions. Comparative studies of several cosmic objects seen by James Webb are starting to give us a better idea of these strange visitors. Astronomers can get a better idea of how the population is distributed by collecting a statistical sample of more accurate mass estimates. This has effects on models of how planetary systems form and how objects are thrown into interstellar space. In turn, these discoveries help us understand how matter moves between stars and the space between them, which gives us a fuller picture of how the galaxy has changed over time. Starburst activity and merging galaxies. During a galactic merging, the gravity forces of the galaxies that are meeting change their original shapes and direct huge amounts of interstellar gas toward the center. This influx of gas greatly raises the density in the area, which then causes stars to form very quickly. This is generally known as an explosion. James Webb has seen these starbursts in many systems that are merging, showing that the rate of star formation can be many orders of magnitude faster than in galaxies that are not merging. The mid-infrared sensitivity of the telescope lets it see through thick dust lanes, revealing groups of young, massive stars that are growing in these rough conditions. By measuring these lines in great detail, we can see that the gas in starburst regions is often very thick and hot. This is because shock waves and turbulence caused by the merging process heat and squeeze the gas a lot. These conditions make it possible for stellar feedback, which includes winds, radiation, and supernova explosions, to make the starburst even stronger. Eventually, the winds blow out the gas and stop more star formation, which can even control how long the burst lasts. Overall rate of star formation, astronomers can now make maps of where starbursts happen in galaxies that are combining thanks to James Webb. High-resolution images shows that these bursts are not spread out evenly. Instead, they tend to happen in groups called knots and along the tide features that were made by the merger. A lot of the time, these areas with a lot of action are also places where gas has been pushed together to form super-strong structures. These clusters are important because they might be the ancestors of the globular clusters that are seen in fully grown galaxies. Scientists can figure out the dynamical past of the merger and how it has changed the galaxy's stellar populations by looking at the shape of starburst regions. The findings made by James Webb help us learn more about the feedback systems that affect starburst behavior. When new stars are born, they release a lot of energy into the space around them. This energy comes in the form of ultraviolet light and supernova blasts. This feedback from stars can cause large-scale movements that push gas out of the galaxy, which changes the starburst's strength and length. By looking at these streams and following the spectral lines of ionized gas and molecule transitions, scientists can see how well the feedback mechanisms control the process of gas turning into stars. Unusual AGN dust, Tauri. The James Webb Space Telescope has given us new and important information about the structure and makeup of the dust Tauri that circle active galactic nuclei, AGN. These new findings challenge the way we usually think about these very busy and powerful cosmic powerhouses. Ultramassive black holes with accretion rings that give off huge amounts of energy power AGN at the center of many galaxies. The center engines are surrounded by the dust torus, a thick, donut-shaped structure made of gas and dust that blocks and reprocesses the high-energy radiation. James Webb's infrared devices are the only ones that can see through the thick dust, which gives scientists a level of detail that has never been seen before. High-resolution spectroscopy in the mid-infrared has uncovered complex emission and absorption features that trace the chemical makeup of the dust. Silicate grains, carbonaceous compounds, and polycyclic aromatic hydrocarbons, PAHs, are among the constituents identified within these tori. The characteristic spectral features, such as the 9.7 micron silicate absorption and emission bands, provide vital clues about the temperature, composition, and distribution of the dust. James Webb's sensitivity allows for the detection of subtle variations in these features, revealing how the dust is processed by the intense radiation field of the AGN. In some AGN, these observations show that the dust grains are not uniform. Rather, they appear to have undergone significant processing, possibly by shocks or radiation-driven sublimation, which alters their size, distribution, and composition. Spatially resolved imaging with James Webb has also mapped the morphology of AGN dust tori, revealing that they are far more dynamic and clumpy than previously thought. Rather than being smooth, continuous structures, these tori exhibit a patchy filamentary texture with gaps and high-density clumps. This clumpiness has significant implications for our understanding of AGN unification models. The presence of inhomogeneities means that the line-of-sight obscuration can vary dramatically even on small scales, affecting the observed properties of the AGN. For instance, some sightlines may allow a direct view of the central engine, while others remain completely shrouded by dust, potentially explaining the diversity observed among AGN types. The kinematics of the dust within these tori have been probed through Doppler spectroscopy. James Webb's instruments measure the subtle shifts in spectral lines as dust clouds move under the influence of the black hole's gravity and the torus's internal dynamics. These measurements indicate that the dust is in a state of turbulent motion, with evidence of inflows and outflows that suggest an ongoing exchange of material between the torus and the central regions of the galaxy. This dynamic behavior is critical for understanding how material is funneled towards the supermassive black hole, feeding the AGN, as well as how feedback from the AGN, in the form of radiation and winds, regulates the structure of the torus itself. Our in-depth study of AGN dust tori with James Webb has bigger effects on how we think about how galaxies change over time, because AGN activity is closely linked to the growth of supermassive black holes and the development of the galaxies that house them. Figuring out what the dust tori are made of is important for understanding how AGNs live and die. Their mass, makeup, and shape, among other things, affect how energy is moved in the galaxy and can have an effect on how stars grow in the center. Silicate vapor in early galactic disks. High temperatures and shock events can turn silicate dust grains into vapor in the turbulence of young galaxies that are changing quickly. This helps make silicate vapor in the space between the stars. This event has big effects on how we think about handling dust and the conditions that exist before planets form. In the earlier stages of galaxy evolution, energetic processes such as supernova explosions and intense radiation from massive stars heat the surrounding gas and dust to extreme temperatures. Under these conditions, silicate grains that are typically found in the solid phase can be sublimated into vapor. James Webb's mid-infrared spectroscopic instruments are specifically tuned to detect the unique spectral signatures of silicate vapor. Key emission features, particularly around 912 microns, are indicative of silicon-oxygen bonds in a gaseous state. These spectral lines provide direct evidence that the conditions in early galactic disks are sufficient to drive the thermal processing of dust. When scientists find silicate vapor, it lets them study the temperature and density structure of early galaxy rings. Researchers can figure out what's going on inside these disks by modeling the different strengths of the silicate emission features. This lets them figure out things like the typical temperatures at which dust is turning into vapor. The appearance of silicate vapor in many young galaxies means that areas close to massive, newly formed stars are hot enough to turn solid dust into gas. This process changes not only what the dust is made of, but also how opaque the disk is as a whole. Less opacity can then change how fast the disk cools and how it changes over time. It can play a part in the start of gravitational instability that can lead to the formation of stars and planets. The high spatial resolution image by James Webb adds to these spectroscopic findings by making a picture of how silicate vapor is spread out across galactic disks. Detailed maps of space show that silicate vapor is not spread out evenly. Instead, it is mostly found in areas that have recently been heated by shocks or near active star-forming groups. This uneven spread lets us follow the energy feedback from huge stars and supernovae, which gives us clues about how well dust was destroyed and rebuilt in the early universe. Astronomers can figure out how star feedback affects the dust lifetime by comparing areas with lots of silicate vapor to areas with lots of cooler, solid dust. The presence of silicate vapor in early galactic disks also has effects on how galaxies change chemically over time. As the silicate grains are worked with, the gas phase may later form back into new dust particles when it gets cooler. This can change the chemical makeup and grain size distribution within the disk. This cycle of destroying dust and rebuilding it has an effect on the general metal enrichment and on future events of star formation. Unraveling reionization-era galaxies. Some galaxies formed in the first billion years after the Big Bang. They were very important in changing the universe from a neutral state to a charged state. James Webb's deep field observations in the near and mid-infrared give scientists access to these faint and faraway objects that has never been possible before. This lets them make accurate readings of their physical properties and the activities that happen when stars form. James Webb's sensitivity allows it to detect the redshifted light from galaxies at extreme distances, pushing observations beyond redshift 10. The spectra of these ancient galaxies reveal key emission lines, such as Lyman A, O3, and HB, which serve as diagnostics for the galaxy's ionization state, star formation rate, and metallicity. By analyzing these spectral features, researchers can reconstruct the physical conditions that prevailed during the reionization epoch. The presence and strength of these lines indicate that many early galaxies hosted intense bursts of star formation, with young, massive stars generating copious amounts of ultraviolet photons. These UV photons were critical in reionizing the surrounding intergalactic medium, gradually transforming the universe into the transparent cosmos we observe today. Even though these galaxies are very small and don't have a lot of light, they have an amazing range of structures. Some look clumpy and uneven, probably because they are still merging, and the early stages of galaxy formation were very chaotic, while others have clearer, more compact cores. This range of structure types is very important for figuring out how galaxies formed in the early universe. By making maps of where star-forming regions are in these galaxies, James Webb helps to show how feedback loops from supernova explosions and stellar winds controlled star formation and affected how these systems changed over time. James Webb's ability to measure these galaxies' continuum emissions also gives us important information about their star populations. Astronomers can figure out how much dust is in galaxies from the reionization era and how old their star populations are by looking at their ultraviolet slopes. A bluer UV slope usually means that the galaxy is younger, has less dust, and is mostly made up of hot, massive stars. Researchers can now figure out how much each galaxy contributed to the reionization process, and how the effect of many faint galaxies may have driven the ionization of the universe as a whole. Additionally, James Webb is instrumental in probing the interstellar medium of these early galaxies. Early indications of heavy elements, such as oxygen and nitrogen, suggest that even these primordial galaxies underwent rapid chemical evolution. This rapid enrichment implies that the first generations of stars were highly efficient in synthesizing and dispersing metals, setting the stage for subsequent generations of star and planet formation. Polar outflows in star-forming regions. Polar outflows in areas where stars are forming give us a moving look at the feedback systems that control how stars are born and how they change over time. Astronomers can see these fast jets and winds with a level of detail that has never been possible before, thanks to the James Webb Space Telescope. This shows how young stars interact with their surroundings in very complex ways. Young stellar objects, YSOs, in these areas cause strong outflows along their rotational directions, sending material into space that forms and changes the interstellar medium. These polar outflows are launched from the vicinity of protostars, where accretion disks feed the growing star. As material spirals inwards, magnetic fields are believed to channel part of the infalling gas into high-speed jets that shoot out along the poles. Observations show that these jets can extend over several light years, carving cavities in the dense molecular clouds from which the stars are born. The information from James Webb is very helpful for figuring out what's going on physically in the streams. Emission lines from charged and molecule species like H2, Colorado, and Phae show how the gas moves and how excited it is. By looking at these lines, we can see that polar outflows often happen near shock fronts. These are places where the supersonic jet hits the surrounding material, heating it up and starting a chain of chemical reactions. These shocks are very important for understanding how energy and motion are moved from the young star to its surroundings, which controls the formation of more stars in the area. In addition to shock diagnostics, James Webb's observations enable the construction of detailed velocity maps of polar outflows. By measuring the Doppler shifts of spectral lines across the jet structures, astronomers can quantify the outflow velocities, which often exceed several hundred kilometers per second. These measurements are critical for determining the mass loss rates from protostars, offering insights into how the ejection of material influences the accretion process. High mass loss rates can help clear the surrounding envelope, potentially determining the final mass of the star and affecting the evolution of the circumstellar disk that may eventually form planets. A lot of research is also being done on the shape of Arctic streams. James Webb's high-resolution pictures show that these jets are not all the same. They have knots, strands, and bow shocks that show that they are ejecting at different times. These kinds of patterns show that the process of accretion onto the protostar changes over time, with busy times followed by quieter times. The fact that stars form in episodes has important effects on how the protostellar disk changes over time and how planetary systems eventually form. When the outflows combine with the material in the surrounding clouds, it can cause secondary star formation by pushing down on gas in nearby areas. This could lead to the birth of new stars. Polar outflows play a critical role in dispersing angular momentum from the protostellar system. As material is ejected along the poles, it carries away excess angular momentum that would otherwise inhibit the collapse of the core. This process is essential for the star to continue accreting material and growing in mass. By studying these outflows in detail, James Webb is helping to refine theoretical models of protostellar evolution and the early stages of star formation. Characterizing Titan's methane lakes and atmosphere. Titan, Saturn's biggest moon, has one of the most interesting environments in our solar system. Its thick, hazy atmosphere and liquid methane lakes make it seem like a strange but interesting place to live. Titan is a great place to study atmospheric processes and hydrological cycles that happen in a climate very different from Earth's. Its atmosphere is thick, full of nitrogen, and is mixed with methane and complex organic chemicals. Thanks to James Webb's high-tech infrared devices, we can look into these things in more detail than ever before, from the spectral signatures of liquids on the surface to the tiny temperature gradients that run across their surface. Observations of Titan have revealed a moon where the atmosphere plays a pivotal role in shaping its surface. The thick, orange-tinged haze, a result of photochemical reactions driven by solar ultraviolet radiation, scatters and absorbs light, creating a persistent twilight over the entire moon. James Webb's high-resolution spectroscopy has allowed astronomers to measure the absorption features associated with methane, providing key insights into the vertical distribution of methane within Titan's atmosphere. By analyzing these features, researchers can determine how methane is transported from the surface to higher altitudes, as well as how seasonal variations affect the overall atmospheric composition. Titan's network of lakes and seas made of liquid methane and ethane is one of its most interesting traits. Most of these bodies of water are near the poles. Some of them are as big as Earth's Great Lakes. With James Webb's thermal imaging skills, scientists have been able to take accurate readings of these lakes' temperatures and emissivities. These readings show changes that could be caused by things like evaporation, precipitation, or even yearly changing. The spectrum data also helps tell the difference between the chemical makeup of the lakes, giving hints about why organic molecules might be more concentrated in some areas. These new ideas are very important for comprehending not only Titan's methane cycle, but also the processes that might cause more complex chemical molecules to form. James Webb has also made findings about how the surface and atmosphere of Titan interact with each other in complex ways. High-resolution pictures show the soft difference between the lake's smooth, reflecting surfaces and the rough, icy ground around them. These changes in the Moon's surface albedo and texture are very important for figuring out its natural past. Scientists can figure out how air chemicals get to the surface and possibly contribute to prebiotic chemistry by making maps of where organic haze deposits are found. With methane constantly evaporating and condensing, the environment is always changing and is both difficult and full of chemical complexity. The detection of cloud formations and transient weather phenomena, such as methane drizzle and localized storm events, provides an understanding of how energy is distributed across Titan's surface. These observations suggest that Titan experiences a form of meteorology that, while vastly different from Earth's, still follows underlying physical principles of convection and condensation. This offers a unique opportunity to test and refine models of atmospheric dynamics under conditions that are extreme, yet analogously informative for exoplanetary studies. Deep-fried Jupiters. There is a group of exoplanets called deep-fried Jupiters. These are usually hot Jupiters that orbit so close to their mother stars that their atmospheres get very hot, which changes their chemical and physical features in big ways. The infrared spectroscopic powers of the James Webb Space Telescope have allowed scientists to study these hot worlds in more depth than ever before. They have found atmospheric components and thermal profiles that test current models of planetary atmospheres. In deep-fried Jupiters, the intense stellar irradiation results in atmospheric temperatures that can soar well above 2,500 K. This extreme heating drives vigorous atmospheric dynamics and triggers a series of chemical reactions that would be impossible under cooler conditions. James Webb's observations have identified absorption features in the near and mid-infrared corresponding to molecules such as ionized iron, silicon monoxide, and titanium oxide. These species, which are not typically observed in cooler exoplanetary atmospheres, indicate that the high-energy environment is capable of vaporizing rock-forming elements. The presence of these ionized metals reveals that deep-fried Jupiters experience thermal dissociation of complex molecules, and even partial ionization of their atmospheric gases. The atmospheric structure of these hot exoplanets is shaped by both radiative and dynamical processes. With the day side exposed to relentless stellar flux, temperature gradients between the day and night sides can be extreme. James Webb's phase curve observations allow astronomers to monitor how the brightness of a deep-fried Jupiter changes as it orbits its star, providing insights into the efficiency of heat redistribution by winds. In many cases, the observations suggest that the heat is not effectively circulated, leading to a scorching day side and a much cooler night side. This contrast drives strong atmospheric circulation patterns, with supersonic winds attempting to even out the temperature differences, a phenomenon that is directly observable through Doppler-shifted spectral lines. The extreme temperatures cause the atmospheres to expand, reducing the overall density and altering the scale height. By analyzing the pressure-broadened spectral lines, scientists can infer the vertical distribution of various chemical species. This vertical stratification is key to understanding how the upper atmospheric layers interact with the intense stellar irradiation and how they might contribute to atmospheric escape. For some deep-fried Jupiters, the observations indicate that significant mass loss is occurring, potentially transforming these planets over astronomical timescales. Deep-fried Jupiters often have unique traits in their thermal emission spectra that are linked to their chemistry not being in balance. Rapid heating can keep the atmosphere from reaching chemical balance, which can lead to too many or too few of some molecules compared to what theory says should happen. Because James Webb has a high spectral precision, it can find these differences, which is very important for weather models. The interaction of photochemistry and temperature processes creates this non-equilibrium chemistry, which shows how the atmospheres of other planets change quickly and dramatically when conditions are very harsh. Wind patterns on gas giants via Doppler mapping. Doppler mapping uses the Doppler effect, which says that the wavelength of light changes based on how fast the source is moving compared to the viewer, to figure out how fast gas is moving in different parts of a planet's atmosphere. Astronomers can measure very small changes in emission and absorption lines using James Webb's high-resolution bands that cover different parts of a gas giant's disk. For instance, the spectral aspects of molecules like methane, ammonia, and water vapor are looked at in great depth. The spectral lines of an area of the atmosphere that is moving toward the camera are blue-shifted, and the lines of that area of the atmosphere that is moving away are red-shifted. The difference in movement across the planet's surface is then turned into a velocity picture that shows the complicated wind patterns in the sky. The ability to resolve the high-speed jet streams and swirls that make up the atmospheres of gas giants is one of the most important advances made possible by James Webb. The polar jet streams on Jupiter have been measured in great detail. These streams can reach speeds of several hundred kilometers per hour. Researchers have learned more about the processes that cause these very fast winds by recording these speeds. These processes include differential rotation, convective processes, and the transfer of angular momentum. In the same way, Doppler mapping of Saturn has shown a stacked structure of wind speeds with changes that match the unique banded cloud patterns seen with the naked eye. Our knowledge of how energy moves from the planet's deep core to its outer atmosphere is getting better thanks to these studies. The dynamic nature of gas giant weather is further illuminated by temporal studies made possible by James Webb. By conducting repeated observations over time, astronomers can track changes in wind patterns, identify transient phenomena such as storms and vortices, and even measure the evolution of long-lived features like Saturn's hexagon. Such time-resolved Doppler maps not only reveal the current state of atmospheric motion, but also offer clues to the processes that drive changes over periods ranging from hours to months. This dynamic perspective is crucial for developing robust models of atmospheric circulation, as it captures the interplay between radiation, convection, and chemical processes that together dictate the behavior of these complex systems. The accuracy of James Webb's Doppler mapping methods has big effects on the study of extrasolar planets. For gas giant exoplanets, knowing how the winds blow can give us clues about the makeup of their atmospheres, how well they move energy around, and even if they have weather patterns similar to those on the giant planets in our own solar system. These new ideas are very important for comparative planetology because they help scientists understand how the atmospheres of faraway, often harsher exoplanets are similar to those of Jupiter and Saturn, which have been studied a lot. Thermal evolution of white dwarf debris disks. White dwarf debris rings are made up of a lot of different types of dust particles. The dust particles themselves cool down, and the white dwarf's leftover luminosity heats them up. As the remains of planetary systems circle a white dwarf, they heat the dust in their rings very quickly through radiation. According to what James Webb saw, the disk's inner parts can get very hot, hot enough to sublimate some volatile chemicals, while the disk's surface parts stay much cooler. To get accurate temperature maps of these disks, researchers can measure the spectral energy distribution across a large range of infrared bands. These maps are very important for figuring out the dust's temperature structure and radial gradient, which in turn affects how stable and how it changes over time. Emission lines and absorption features corresponding to silicates, carbonates, and metal oxides provide clues about the composition of the dust grains. The thermal properties of these minerals determine how they absorb and re-radiate energy, affecting the overall temperature distribution. For example, crystalline silicates, which form under high temperature conditions, tend to exhibit sharper spectral features than their amorphous counterparts. These details help constrain models of dust grain growth, processing, and eventual destruction within the disk. Temporal monitoring of white dwarf debris disks is another area where James Webb has made significant contributions. The telescope's ability to capture time-resolved mid-infrared images allows astronomers to detect subtle changes in the disk's brightness and structure over time. Variations in thermal emission can be linked to dynamic processes such as collisional cascades, where dust grains continuously fragment into smaller particles, or accretion events, where dust is gradually drawn onto the white dwarf's surface. By tracking these changes, researchers can estimate the mass loss rates from the disk and assess how rapidly the disk evolves. This time domain study provides critical insights into the life cycle of debris disks and the fate of the planetary material that they contain. James Webb's observations have shed light on the mechanisms by which these disks interact with their host white dwarfs. The intense gravitational field of a white dwarf not only disrupts incoming bodies, but also influences the disk's overall structure. High-resolution infrared imaging has revealed that many debris disks around white dwarfs are not uniform. Instead, they exhibit rings, gaps, and asymmetries. These features may be indicative of ongoing planetesimal collisions, or even the gravitational perturbations from surviving planetary bodies. Tracking rogue planetary mass objects in star clusters. Most of the time, rogue planets in star groups are thought to have formed either by turbulently ejecting from their early systems or by breaking apart during star formation, creating objects with masses below the limit for hydrogen burning. Astronomers have been able to do regular surveys of dense clusters using James Webb's high-resolution images and deep sensitivity in the near and mid-infrared. These surveys have shown a population of low-mass objects that could not be seen with ground-based telescopes before. The unique infrared colors of these items show how their spectral energy is distributed, which directly limits their effective temperatures, luminosities, and surface gravities. Researchers can figure out how heavy and old rogue planets are by matching what they have seen with theoretical models of evolution. This lets them put them in the same category as stars and exoplanets that are bound to them. Many rogue planetary mass objects exhibit signatures of molecular absorption bands from water vapor, methane, and carbon monoxide. These features are indicative of cool atmospheres, where chemical equilibrium processes dominate. James Webb's spectrometers can resolve these bands with high precision, revealing subtle differences in composition that may be linked to formation history and environmental factors. For instance, variations in the abundance of methane can help distinguish between objects formed in isolation versus those ejected from young planetary systems, where accretion processes and irradiation by a host star may alter their primordial atmospheres. The way that rogue planetary mass objects are spread out in star groups also tells us a lot about how these systems have changed over time. With James Webb's wide-field imaging, these items can be mapped across groups, showing patterns that suggest they have been processed in a dynamic way over time. It makes sense that rogue planets are more likely to be found in the outer parts of some clusters. This is because dynamical interactions and gravity encounters in the dense core can push lower mass objects to the edges. This radial segregation shows how energy is distributed within clusters and how the number of stars affects the preservation of objects below the stars. Astronomers can also figure out if these objects are still gravitationally bound to the cluster or if they are moving away into the interstellar medium by studying their kinematics. To do this, they use proper motion measurements and Doppler changes from spectral lines. James Webb observations have provided a clearer picture of the mass function at the low-mass end of the stellar population. The detection of numerous rogue planetary mass objects in clusters refines the initial mass function, IMF, a fundamental quantity in astrophysics that describes the distribution of masses at birth. The shape of the IMF at these low masses has significant implications for theories of star formation and the efficiency of the fragmentation process in molecular clouds. By combining data from multiple clusters, James Webb is helping to determine whether the formation of rogue planets is a common outcome of the star formation process or a relatively rare event. Monitoring supernova remnants. Scientists can see through dense clouds of dust that block optical wavelengths from seeing supernova remains when they use James Webb's near and mid-infrared equipment. This infrared picture shows the whole structure of the residue, including filamentary networks, clumpy ejecta, and areas of material that was shocked and heated up. Researchers can figure out how fast the residue expanded and how the energy was distributed by mapping these features. high-resolution spectroscopy makes it possible to measure very accurately the main emission lines that come from charged elements like iron, oxygen, neon, and sulfur. These spectral lines help us figure out the temperature, density, and makeup of the shocked gas. This lets us get a better picture of how strong the explosion was and what the parent star's nucleosynthetic outputs were. James Webb observations have provided critical insights into the role of shock waves in supernova remnants. As the blast wave from the explosion propagates through the interstellar medium, it compresses and heats the surrounding gas, leading to the formation of shock fronts that can accelerate particles to relativistic speeds. The detection of synchrotron emission and the mapping of these shock fronts in the infrared provide evidence for the efficient acceleration of cosmic rays in these environments. Moreover, by monitoring changes in the spectral properties of the remnant over time, astronomers can study the cooling processes that follow the initial shock heating, such as radiative cooling and thermal conduction. These processes govern the evolution of the remnant and influence how the ejected material mixes with the ambient medium. One of James Webb's main strengths in studying supernova remains is that he can keep an eye on time. Researchers can see how the remnant's shape and size change over time by looking at it over and over again. This time domain data is very important for understanding how the explosion changed over time, including how the uneven spread of the ejecta affected the growth of the remnant. For example, changes in the brightness and structure of filaments and knots within the residue can show differences in density or makeup in certain areas. This can help us understand how the progenitor star was heterogeneous and how the explosion happened. By accurately measuring the abundances of heavy elements such as iron, nickel, and silicon, scientists can test models of stellar evolution and supernova nucleosynthesis. The spatial distribution of these elements within the remnant offers clues to the mixing processes that occurred during the explosion and subsequent expansion. Exotic molecules and the quest for life beyond Earth. Because the James Webb Space Telescope is so sensitive in the infrared range, scientists have been able to find many complex molecules in the atmospheres of other planets. This gives us a whole new way to look at the chemistry of these faraway worlds. This discovery not only changes the way we think about how planets form and change over time, but it also makes us wonder if there might be life beyond Earth. With its unmatched spectral powers, JWST has shown us a complex web of organic molecules that we thought were only found in labs on Earth or in the dusty remnants of our solar system. Astrobiology is changing because of these findings. Scientists are now trying to figure out which of these chemicals could be the start of life, or even direct biosignatures. The most important thing about these discoveries is that complex organic molecules have been found in the atmospheres of several exoplanets. These are molecules made up of carbon, hydrogen, oxygen, and nitrogen in different arrangements. JWST has been able to find absorption patterns that match to a number of different organic species by taking high-resolution spectra over a wide range of wavelengths. Molecules like methane, acetylene, and even hints of more complicated hydrocarbons have been seen in places where high temperatures and strong radiation were thought to make it impossible for these molecules to form. The fact that these molecules are found, especially in hot, irradiated atmospheres, goes against what we usually think about chemical equilibrium. It suggests that stellar irradiation, photochemistry, and vertical mixing, which are not in equilibrium, play a big part in shaping the atmospheres of exoplanets. Potential links to prebiotic chemistry are one of the most interesting things about these findings. Finding complex organic chemicals in places that are similar to Earth's early days makes it more likely that the building blocks for life are more common in the galaxy than was thought before. These results are very important for making models of planets' atmospheres better, which in turn affects the search for places where people could live. If we can figure out that certain molecular ratios or chemical abundances are linked to settings that are good for life, then JWST's observations will help guide future missions that are looking for biosignatures. JWST has allowed scientists to probe the vertical structure of exoplanetary atmospheres with unprecedented detail. By analyzing the depth and shape of various molecular absorption features, researchers can infer how molecules are distributed with altitude. For example, the detection of stronger methane absorption in the upper layers of some exoplanets suggests that photodissociation is actively altering the atmospheric chemistry, while the presence of complex hydrocarbons deeper in the atmosphere hints at efficient vertical mixing processes. These vertical profiles are crucial for understanding the energy balance, weather patterns, and overall climate of these distant worlds. Such detailed insights help distinguish between different atmospheric models and set constraints on parameters like temperature gradients and chemical reaction rates. Even chemicals that weren't thought to be possible on some exoplanets because of their harsh conditions have been found. Some JWST data have hinted at the presence of molecules like phosphine, which is usually linked to biological processes on Earth. This has led to arguments and more research into the non-biological processes that might make these molecules in environments outside of our solar system. Scientists have to rethink long-held ideas about chemical stability and reaction networks in the atmospheres of planets because of these unexpected findings. They also show how important high-sensitivity data are for finding small details that can have big effects on how we think about possible habitability. Using JWST's data, researchers are now comparing the atmospheres of many different types of exoplanets, ranging from hot super-Earths to gas giants with a lot of gas. The goal of these kinds of studies is to find out if there are common chemical patterns, or if the amounts of molecules seen change a lot from one planetary system to the next. It's important to understand these trends if we want to figure out how planets change chemically over time, and if there are conditions that make life more likely to start. Detection of these exotic molecules has implications for the design of future space missions. The insights gained from JWST's spectroscopic surveys are helping to refine the target lists for next-generation telescopes and interstellar probes. By identifying which exoplanets exhibit promising chemical signatures, researchers can prioritize those worlds for follow-up observations aimed at searching for direct signs of life. In this way, the quest to understand exotic molecular chemistry is directly tied to the broader search for extraterrestrial life, ensuring that future efforts are focused on the most promising candidates. Revolutionary insights into stellar evolution and death. Comprehensive research into planetary nebulae, the bright rings of ionized gas that dead low to intermediate mass stars throw off, has been one of the most important steps forward. Because it can see infrared light, JWST can see through the dusty layers that usually cover these nebulae. It can then see complex structures that show how the star's mass has been lost over time. High-resolution spectroscopy has found many emission lines from elements like carbon, nitrogen, and oxygen. This has helped scientists make accurate maps of these nebulae's temperature, density, and chemical makeup. This level of detail not only helps us understand how mass is lost, but it also gives us important information about how long it takes for these stars to change from the asymptotic giant branch phase to their final white dwarf state. In the realm of massive stars, JWST has also focused on Wolf-Rayet stars, which represent a brief yet turbulent phase in the life cycle of the most massive stars. These stars are characterized by their intense stellar winds that strip away their outer layers, exposing the products of nuclear fusion from deep within their cores. JWST spectroscopic data reveal broad emission features dominated by ionized helium, nitrogen, carbon, and oxygen, offering insights into the extreme conditions within these stellar winds. Detailed line profile analysis has enabled researchers to measure wind velocities and mass loss rates with unprecedented accuracy. This information is crucial for refining theoretical models that describe how these stars eventually explode as supernovae, potentially leaving behind neutron stars or black holes. Supernova remnants, which are the ghosts of stars that died in explosions, are another place where JWST has done a great job. The mid-infrared imaging from the camera has seen through the thick, cloudy dust that usually hides these remains from visible light. It has shown filamentary networks, shock fronts, and clumpy ejecta in a lot of detail. By looking at the emission lines from heavy elements like nickel and iron, scientists can figure out how these elements are moved around in the space between stars and track the nucleosynthetic outputs of the supernova explosion. These kinds of studies are very important for helping us understand how galaxies improve chemicals and how recycled materials keep the cycle of star formation going. Additionally, JWST has recorded how the remains have changed over time, giving us time-lapse views that show how the shock fronts have moved and how the objects are cooling. These studies of time help to assess models of how energy is lost and how radiative cooling works in supernova remnants. This gives us a better idea of the physical processes that control what happens after these huge explosions. As we conclude our odyssey through the discoveries of the James Webb Space Telescope, we are left with a profound sense of wonder and renewed curiosity about the universe. Every observation, from the birth of ancient galaxies to the subtle interplay of elements in exoplanet atmospheres, has expanded our cosmic perspective and deepened our appreciation for the intricate beauty of the cosmos. The insights provided by James Webb remind us that our universe is an ever-evolving tapestry of creation, destruction, and rebirth. These revelations inspire us to keep exploring, questioning, and dreaming, knowing that each new discovery opens the door to even more mysteries. If you found this journey through the cosmos as fascinating as we did, make sure to subscribe for more deep dives into the universe. Leave your thoughts and questions in the comments below, and share this video with fellow stargazers. Let's continue pushing the boundaries of what we know together.